Welcome again. Today we will discuss chromium and manganese based reagents in organic synthesis. So this is chromium and manganese, they are side by side. So this is fourth row and chromium is present in 6B group and manganese in 7B. So first we will discuss chromium based reagents and the reactions, nucleophilic substitution reactions of chromium arene complex. Then we will discuss ring lithiation, chromium arene complexes in asymmetric catalysis, because if it is disubstituted then it is chiral, that we will discuss. Catalysis, chromium carbene complex, CC cross coupling reactions, and finally Takai olefination. So chromium arene complex, most eta 6 arene CrCO3 complexes are air-stable yellow or red crystalline compounds and can be easily prepared from the free arenes by thermolysis with hexacarbonyl chromium in a high boiling solvent. So these can be easily prepared by reacting hexacarbonyl chromium with the arene. So this is the structure, you can see here 3 carbonyl are attached to chromium, and this group can be facilitated, solubilization is possible, then configuration is stable, and this is enhanced acidity, that we will see also, the enhanced acidity, and shielding of the complex ligand X is equal to Cl Bri, enhanced acidity of this proton also, and facilitated oxidative addition of the palladium 0 at this group. We will see different reactions and facilitated attack of nucleophiles and radicals, that also we will see. There is a nice review, Chemical Society review 2007. So solution of chromium arene complexes are usually sensitive toward oxidation, particularly in light. The sensitivity can be utilized for decomplexation reaction under mild oxidative conditions, as for example air, sunlight, iodine or ferric salt, allowing an efficient release of the metal free organic ligand. So it is possible to remove the chromium complex by under sunlight, air or iodine or ferric salt. Now if a non-symmetrically 1,2 or 1,3 disubstituted arene, that means this kind 1,2 or 1,3 arene ring is complex to chromium, the resulting molecule lacks symmetry elements. The result is a chiral compound with a plane as the origin of chirality. So this is called planar chirality. We will see also the examples. Now first we will discuss nucleophilic substitution reaction. The strong electron withdrawing ability of the CrCO3 group makes haloarene chromium complexes prone to suffer nucleophilic attack. So this is actually EWG, electron withdrawing group. So nucleophilic substitution is possible on the arene ring. The aryl chromium tricarbonyl complex can also undergo nucleophilic aromatic substitution with carbon nucleophiles also is possible. And the mechanism involves the addition of the nucleophile to the aromatic ring to generate a chromium stabilized carbanionic complex. The metal stabilized anion intermediate can be decomposed by reaction with iodine or by protonolysis to give substituted products. So with iodine you can remove the chromium. However, the addition of nucleophile can also be reversed on heating the carbanion aryl chromium tricarbonyl complex. So by heating also, if the addition is reversible. So this is the arene complex, arene chromium complex. Here 3 carbonyl is there. Now nucleophile adds like this one 1,3-dithiol lithium, and you get this eta 5, and this negative charge is stabilized by chromium. Negative charge stabilized by chromium. And with iodine you get the aromatization. Aromatization and elimination of CrCO3. So if you put just iodine, then you get. So, it is very easy method to get a group like this nucleophile with just addition and then followed by iodine treatment. This was published in JACS 1979. Some more examples. Nucleophilic addition to methoxy substituted arene CrCO3 complexes is known to give meta substitution. We will see. So, if there is a methoxy group is present in the arene, then the nucleophile adds to the meta position. So, this is the meta. Here the attack will take place and you get this. And after trifluoroacetic acid, you get the cyclohexadiene. So, earlier we have seen the aromatization happened with iodine, but if you put acid, then you get cyclohexadiene system with the nucleophile here. This was also published in JACS 1979. So, after the nucleophilic attack, several pathways are possible. Oxidation, as we have seen, iodine, ferric salt, iron salt, oxygen gives an arene with a new substituent, substitution of CH. Reaction of the intermediate with other electrophile traps the intermediate only when the nucleophilic attack is irreversible. If it is reversible, the original arene complex is recovered upon electrophilic attack. And if there is no leaving group, the reaction of the cyclohexadiene intermediate with strong acids or carbon electrophiles is de-aromatization, resulting in a cyclohexadiene. So, this is happening here, that cyclohexadiene is forming after treatment of a strong acid like trifluoroacetic acid. Some more examples of nucleophilic substitution. Tele substitution. Tele means further from the group, further from the group already present. So, like meta, para, that is called tele substitution, is the major pathway in air reactions of orthoalkylated eta 6 anisols complex to CrCO3. Addition of N-butyl lithium to tetraline derivative complex in THF HMPA gives a high yield of complex. These reactions are tele-meta substitution with methoxide as the leaving group. So, this is the reaction, this is tetraline derivative, tetraline chromium complex. So, if you see, this is a anisole and there is also another methoxy and TMS group. Now, butyl lithium, if you put butyl lithium, this butyl group adding at this position, and after aromatization you get this. So, we will see the details mechanism. So, if you add butyl lithium, then it is adding here, and this is also chiral. So, butyl lithium is coming from the top side because chromium is down. So, butyl is coming from the top side and attacking in this carbon selectively. Then you get this anion which is stabilized by chromium. And now, if you treat with water, aqueous workup, then what happens? This anion getting protonated and the aromatization will happen now. You see, this methanol is eliminating. So, this hydrogen is eliminating and this methoxide. So, ultimately methanol is eliminating. So, aromatization is happening and you get the butyl substituted chromium complex, and this also chiral. This was published in Angiochemy 1996. Ring lithiation is also possible. Aryl chromium tricarbonyl complexes can be used for the synthesis of alkyl substituted products by treatment with organolithium reagents, followed by treatment with electrophiles. So, this is an important reaction, that this is the arene chromium carbonyl complex, and with N-butyl lithium you can deprotonate. So, this acidity of the benzene ring increase because it is coordinated with chromium. So, with N-butyl lithium you can deprotonation is possible. So, deprotonation on the ring, and this one can be used for electrophilic reactions. So, different electrophiles like carbon dioxide, you get CO2Me. Of course, here you have to add methyl iodide also, methyl iodide addition. Then iodine, if you put iodine, then you get I in the aromatic ring. If you put dimethyl silyl chloride, then you get TMS group in the ring and you get 94% yield. So, this is a very useful method for getting this kind of compounds. Now, enantioselective version also possible. If the ring is disubstituted after lithiation, then you can get the chiral product. So, the ring deprotonation of aryl chromium dicarbonate complex occurs to allow the regioselective preparation of a variety of alkylated complexes under mild conditions. Highly enantioselective deprotonation of prochiral substrates is possible in the presence of chiral bases. Like here, this is monosubstituted complex, and now after lithiation followed by TMS quenching, you get this chiral product. So, this is chiral product. So, if you know the LDA was diisopropyl, this is LDA, and this is one methyl group is displaced by phenyl, and this is also C2 symmetric. So, this is chiral base, and with chiral base you get a selective lithiation, also enantioselectively, and you get this product TMS substituted product in 83% yield with 86% E. Again you can put another equivalent of simple butyl lithium, because this is now chiral. So, N butyl lithium, if you put this lithiation takes place, this hydrogen is deprotonated and tributyl tin chloride reaction, the tin substituent coming here, and this product is from 82%. So, this is also chiral. So, the enantioselective lithiation is possible with chiral base. Now, we will discuss this chiral chromium complexes in asymmetric catalysis. So, chromium arene complexes have been successfully employed as chiral ligands for catalytic enantioselective hydrogenation, carbon-carbon coupling reaction, allylic sulfonation, hydrosilylation and hydroamination. So, many reactions can be performed with these chromium arene complexes. Example, rhodium catalyzed enantioselective hydrogenation of methyl acetamidoacrylate using various diphosphine ligands based on benzene or indene chromium dicarbonate complexes. Like this is enamide. We have seen this kind of substrate earlier. So, this is enamide now with 0.1 mole percent rhodium cyclooctadiene Cl whole 2, 0.2 mole percent of L2. So, this will see the structures chiral ligand. So, this is chiral, and 1.5 bar hydrogen THF 25 degree centigrade, you get the hydrogenation of the enamide and you get this chiral product. So, these are the chiral alpha amino acid derivative. And now we will see the ligand structure. So, all of these are diphosphines. Now, this is ferrocene based. So, this is a phosphine, here is a phosphine, and this with ferrocene phase, this is called Josephus, you get 88% E. Now, this is our chromium arene complex, tricarbonate complex, here this phosphine is there, this is phosphine, this is a chiral center, and this also planar chiral. So, this one is giving Danifos 95% E for this product. Now, if you make another cycle, that is the indene derivative, here phosphine, then you get indene diphosphine, which is giving 88% enantioselectivity for this product. So, this Danifos catalyst is the best for this enamide hydrogenation, and you get 95% enantiomeric excess. So, this was published in Journal Organometallic Chemistry 2006. Some more reactions in asymmetric catalysis, like Heck reaction. So, this is mistake, this should be single bond. So, this is dihydrofuran. So, dihydrofuran reacting with this triplet, aryl triplet with 6 mole percent A. So, A is this is also diphosphine that earlier we have seen. Here a phosphine is there, R3 is equal to PCOI2, and R2 also is a phosphine. And there is an additional tertiary butyl substituent in the para position, and with this ligand, and this is the catalyst 3 mole percent palladium acetate, 2 equivalent of diisopropyl ethylamine THA, you get 20 to 60% yield of this Heck coupling product, and the enantiomeric excess is 42 to 62%. So, what happening after this coupling, this product is forming first because we know the head coupling, the double bond will isomerize, and this will isomerize this one because this will be stabilized more. So, first this is forming and then this is isomerization is happening, and this product is obtained in 42 to 60% enantiomeric excess. This was published in Synthesis 2006. Also, a highly selective diol planar chiral chromium as deep cellular catalyst. This one the catalyst. So, here you can see this chromium is present, and this is the diol aluminum. So, aluminum is good Lewis acid, and this Lewis acid is activating the aldehyde group, and this acraldehyde, when it is treated with this diene, this cyclic product is forming in 86% enantiomeric excess. So, this is the chiral center, and when it is treated with cyclopentadiene, then you get a bridge compound. So, this is bridged, and endo is the major. So, this is the endo structure, CHO is down, endo is forming in 85:15 ratio NDXO, and the enantiomeric excess of endo isomer is 85% E. This was published in Tetrahedron Asymmetry 2000. Chromium arene complexes, now it can be applied for natural product synthesis also, like this one. This is not chiral because this is monosubstituted, so this is achiral. Now, if you make a imine, so this is chiral, this is valinol, and this is chiral imine. Chiral imine is formed here. Now, if you add vinyl lithium to this aromatic ring, now this will add to here, and this addition will be enhanced selectively like this one, and after that this anion will form here. This anion you can react it with carbon monoxide, methyl iodide, so that you get a ketone, and that ketone alpha position again you can treat with sodium ethoxide, methyl iodide, you get the methyl, and this product is from 95% E, and in this process this CrCO3 also is eliminated. So, first addition here, then the, so first nucleophile, then the electrophile, that is the carbon monoxide and methyl iodide, you get the ketone, and then the alpha functionalization of the ketone with sodium ethoxide, methyl iodide, and these two hydrogen and methyl, so these two are in the cis position, and this intermediate can be converted to the natural product. This is the plus version, as plus acetoxy TUB-furan. Now, the other enantiomer also you can form. So, here you make a achiral imine. So, this is achiral imine because cyclohexylamine is added, and now with a C2 symmetric ligand. So, this is C2 symmetric bis ether, PH, OMe, and with this C2 symmetric bis ether, the addition of this vinyl lithium also you can do in chiral fashion. So, here the chiral ligand is present, and with this you get the other enantiomer, but the enantiomeric excess is low, 76%. So, addition second by methyl iodide, carbon monoxide, HMP, same reaction, and then the alpha functionalization sodium ethoxide methyl. So, you get a chiral quaternary center, and this hydrogen methyl is in the opposite phase now. So, these two are enantiomer. So, this can be converted to the minus one, minus acetoxy TUB-furan. This was published in JACS 2003 1255642. Now, we will see simple catalytic reactions also can be carried out. Arene CrCO3 is a good source for the generation of free CrCO3 unit that catalyzes useful organic transformations. For example, the selective U1,4 hydrogenation of U1,3-diene gives J-configured alkenes. Only U1,3 dienes that can adopt S-cis-side conformation is compatible under this condition. Isolated double bonds are not affected. So, isolated double bonds are not reacting, while naphthalene CrCO3 complex catalyze U1,5 hydride shift. So, we will see this reaction. So, this is diene, and you can see this is linear. So, this can take S cis-side conformation. So, S cis-side conformation is possible, and 1 mole percent anisole CrCO3. So, anisole is this, anisole and CrCO3, this complex, and this is also achiral because monosubstituted with hydrogen 60 atmosphere, THF 120 degree centigrade 5 hours, you get this olefin. This is Z configured, and the yield is 100%. So, this is quite good that you get high yield for this olefin, Z olefin. Also 1,5 hydride shift is possible with this naphthyl CrCO3. So, this is naphthyl and CrCO3. With acetone 20 degree centigrade, you get this. So, what is happening? This hydride attacking here, then this, because this carbocation will be stabilized by this oxygen OT-base group. So, this 1,5 hydrated shift, this also now dying, and this product is forming in 75 to 97% yield. Chromium carbene complex, metal carbene complexes have received a great importance in organic synthesis. Chromium forms Fischer type carbene complexes. Synthesis of Fischer carbene complexes, standard Fischer route, this is the most direct and general approach to Fischer carbene complexes. Limitations are the availability of organolithium compound and the alkylation reagent. So, earlier we have seen that the chromium hexacarbonyl when reacted with arene, then the arene chromium complex is formed. Now, we will react this chromium hexacarbonyl with lithiated alkyl lithium, and then you get the carbene. So, this is the what is happening with the hexacarbonyl. One carbon monoxide is reacting with R1Li, and when this reaction is taking place, then you get this carbene. So, this is one carbon of carbon monoxide, and you get this intermediate. Now, this OLI can be reacted with an alkyl halide, so that this alkoxy substitution is possible, and this can be replaced with thiol. So, if you react with thiol, then you get the SR3 group here, the carbene SR3, also with secondary amine. Then you get the amine containing carbene complexes. So, these reactions are useful, and you can generate these carbene complexes very easily. Now, we will see the reactions of these carbene complexes. First, we will discuss ligand centered. The ligand is involved in the reaction. So, this carbene can be in resonance form with this, because this metal can take an anion also, because it is coordinated with carbon monoxide, which are pi acceptor. Also, this one, this hydrogen will be acidic, so with base you can deprotonate. Also, nucleophile can be reacted, that we have seen already the substitution reactions here, and electrophile can also react with oxygen. That kind of reactions also is possible. So, first we will see this kind of reactions. The nucleophile is reacting at the carbene. So, with amine, this intermediate is forming, because this anion is stabilized by chromium, and now methanol is eliminating, you get this amine here. Also, this is bidentate reagent, bidentate. So, this one will react here, and this one will react here, because the methoxy will displace by this. So, ultimately you get this cyclic product, cyclic, also the carbene is present. So, this oxygen is this oxygen, and this phenyl. So, this is very important that you get this product, and this was published in Journal of Chemical Science, Chemcom, 1993. Now, bond formations via metal carbene anion. So, this is methyl acetate, and the pK is 25. On the other hand, this carbonyl is displaced by chromium carbene, then this pK is 12. So, because this hydrogen is acidic, so when it is carbene complex, then the hydrogen is very much acidic, because it is in the resonance, this chromium can take a negative charge, and so this is because the conjugate acid stabilization, conjugate base. So, conjugate base stabilization, and that is why you get the high acidity. So, this is chiral carbene, because this is a chiral imide is present. So, this is imide, and this carbonyl also will be coordinated with chromium. And now, as we told that this hydrogen is acidic, so with N-butyl lithium you can deprotonate this one, and then you can react with benzaldehyde. So, this reaction, that is the aldol. So, aldol reaction, and aldol reaction can be done in enhanced selectivity. So, newly generated chiral center is this OH will be down, because this is the pH up, and after that if you treat with acetic acid and cerium 4, then you can eliminate this carbene, and this carbene, actually this carbene is going to carbonyl. So, this carbonyl is generated from this one. So, carbene is going to carbonyl, and you get this compound in high yield 60%, moderate yield, and greater than 96% diastomeric excess. So, D is diastomeric excess. So, greater than 96%, this is very important reaction, you get high diasto selectivity, and this was published in JOC 1994. Not only reacting with aldehyde, epoxide can also be reacted, and epoxide can be reacted at the less substituted carbon atom, and after that the epoxide opening happen, and you get this O lithium. And what happens, this O lithium also reacting here, this O lithium is reacting here. So, this exchange happens, methoxide is replaced by this O lithium, and you get this cyclic carbene is forming here, and this was published in JACS 1993. Now, we will discuss cycloaddition reactions. So, if this earlier we have seen methyl, now if you put a double bond here, so what will happen? This double bond is electron deficient. So, this double bond is electron deficient, and suitable diene. So, electron rich diene. So, this diene, if you see the structure, there is a OTBS methoxy group. So, this is called Danishevsky diene, and this diene, after reaction with this one in DCM room temperature and 80% single isomer, you get this one. And here you see this CH3 and A in the double bond, they are trans, and here also they are trans. So, this is trans, and we know this reaction is happening like this: OTBS OCH3, and if you have this CH3, this is the carbene, chromium CO4 is the R. So, the reaction will happen like this, so that you get this product. So, the double bond will be, the carbon will be connected with OTBS group. This was published in JOC 1994 6882. Also, Diels-Alder reaction of boroxy carbene complexes also is possible. So, this one, now here you have to generate a carbene. So, this is the vinyl bromide, and also an tertiary amine is present, and with tertiary butyl lithium this metal halogen exchange will happen, metal halogen exchange with tertiary butyl lithium, and that vinyl lithium will add to the hexacarbonyl chromium to generate this carbene, and this alkoxy group will react with BF3 etherate, and this six membered ring is formed. And in this six member, this boron is coordinated with oxygen as well as the amine, and one fluorine also is liberated. And now if you react this one, so this is electron deficient, and this diene is electron rich. So the Diels-Alder reaction will happen, and this Diels-Alder reaction is carried out in minus 78 degrees to room temperature, you get 85% yield, and after 3 normal HCl you get this ketone. So this also you can draw like this in pH methyl, and this is your the A CrCO5 carbene. So the reaction will happen like this. So you get an enamine. Here a methyl, and here the substituent. So here a quaternary center will form, and this enamine can be hydrolyzed to ketone, because this enamine can be converted to imine with acid. So 3 normal HCl, this enamine is going to carbonyl with 3 normal HCl, and this ring is still there. Now if you put it HBr, so HBr is stronger acid, HBr dichloromethane room temperature. Now you can hydrolyze the carbene and you get a aldehyde here, and this BF3 is eliminated, you get this product in 85%. So most likely this one, this will be aldehyde acetal, and this finally going to the aldehyde moiety, and this was published in JACS 1998. So this is an important reaction because you get this kind of compound and in the diastereoselective fashion. So far we have seen the reaction at the ligand. Now we will see the metal centered reaction. Reactions with olefins, cyclopropanation first we will discuss. So this is the metal carbene, and this can eliminate one carbon monoxide, then the tetracarbonyl is present, and this tetracarbonyl can react with a olefin. So olefin, and then this 4-membered ring will form, 4-membered ring, and this 4-membered ring can give olefin metathesis products. Also it is possible to give cyclopropanation, because this one can react here, and this was published in Organometallics 2002. So we will see now examples of cyclopropanation reactions. Chromium carbene complexes used in cyclopropanation reaction. So this kind of chromium carbene complexes, so all cases you see methoxy is present because it stabilizes the intermediate, you will see, and suitable olefins. Of course electron withdrawing group is better, also alkyl group can be present, also 1,1 disubstitution is possible, also R1 is possible, R1 is equal to alkyl aryl R1 R2, and when this trisubstituted is present, then it is requires stronger electrophilic metal carbenes. So some examples we will see. So this methoxy is present, also there is an external double bond, but that will not take part in the cyclopropanation, and the ferrocene motif is present, and this is the normal olefin with DMF 152 degrees centigrade, you get 88% yield and 97% diastereomeric excess. So you get 97% diastereomeric excess. You see this group and this group they are trans, and methoxy is in the cis of this group. So, this is the cyclopropanation happen, and this is much simpler. Carbene, a methoxy group is there, methyl group is there, and this is the diene, and here selectively this terminal double bond will react, and after the cyclopropanation you get this. Here also this methyl and this group are trans. So, we will see why so much good diester selectivity you get. So, we will see the model now. This carbene react with this diene, what happens, this 4 member ring is forming. So, this chromium like this 2 plus 2, you can think of 2 plus 2 reaction here, and now this is forming, and here this methoxy and this diene are in the same side, and that because this methoxy can coordinate also, this coordination is possible. See, this is the coordination of the methoxy with the chromium as well as the double bond. So, this will be much stable and this process will be favored. So, the methoxy and this they are in the same side and methyl is far. On the other hand, when methoxy is far, it cannot coordinate with chromium. So, this coordination will not happen because methoxy is far. So, this will be less stable and this process is disfavored. So, you get high diester selectivity for these reactions, and this was published in JACS 1991. Now, we will discuss another reaction, that is benzanylation. So, this is also metal centered. The dot benzanylation is an alternative approach towards the synthesis of chromium para dioxygenated arene complexes. So, here this is also same like earlier we have seen carbon monoxide element, you get this, and this can react with alkyne. So, this is the alkyne, and it can make first coordination, this is the coordination, and then the addition. So, this addition is taking place such a way, there is RS side it is coming. So, this carbene is reacting at the RS side, and this stereochemistry is such that this RS and this chromium will be in the cis. So, that minimization of interaction is possible. So, RS and RL are trans and this RS and chromium are at the cis. So, this kind of thing is possible, and now if you see this carbene has changed now, carbene come to this carbon now. So, chromium carbene is now this carbon, and after that what will happen, one carbon monoxide will react and you get a ketene. So, 1 out of 4 carbon monoxide 3 are there and 1 carbon monoxide reacted here. So, the insertion happens and so that you get the ketene, and chromium then coordinates with the double bond, and this is very important intermediate, this ketene, because immediately this will be reacted with the aromatic ring to get another ring. So, this kind of reaction will happen and you get a carbonyl, of course, you get a carbonyl here, and after aromatization, so this aromatization will happen. And you get this dioxygenated. So, this is para dioxygenated arene complex. So, this is a very important reaction, that a chromium carbonyl aryl reacting with an alkyne and giving a bicyclic compound. Now, we will see cross coupling reaction. Organochromium species are useful in coupling an aldehyde to an allylic moiety, where the more substituted carbon of the allylic moiety attaches to the carbonyl carbon. The organochromium species is formed by the oxidative addition of chromium to allylic halide. This reaction is known as the Nozaki-Hiyama coupling reaction. So, this is allyl bromide, this is aldehyde, this is ester. So, selectively it is reacting to the aldehyde, and with chromous chloride 2 equivalent THF room temperature, you get this secondary alcohol with the allyl group in 75%. So, this is allylation reaction, allylation. So, what is the mechanism? First the allyl radical is forming chromium 3, then allyl anion, and this is stabilized by chromium 3, and now the reaction will take place, and this will take Zimmermann-Traxler transition state. So, like this way it will react. This is the new bond forming, and after that you get this one OCrOx2. Of course, after hydrolysis you get the alcohol. After hydrolysis you get the alcohol with the allyl group, and this was published in JACS 1977. And last for chromium we will discuss Takai elimination. So, Takai elimination describes the organic reaction of an aldehyde with a diorganochromium compound to form an alkene. The reaction product is vinyl halide. So, this is benzaldehyde with 2 equivalent CHX3. If iodine, that is called iodoform, 6 equivalent CrCl2 THF, you get this vinyl halide, and selectively E is formed as measure. Z is 95:5, and when X is equal to I, the 0 degree centigrade reaction occurs and you get 87% yield for this vinyl halide, and when X is equal to Br, you need room temperature 1.5 hours and you get 32% yield. So, when X is equal to I, then the reaction beta reaction. In the mechanism, because iodine can be displaced by chromium easily, so this is iodoform with chromium 2, so this is oxidative addition is happening. So, 2 iodine will be reacted and generate this one CCr3. Now, it will react with aldehyde and will generate this kind of intermediate, and this is the extra chromium. So, here these 2 chromium are present in the nucleophile and it is reacting with the aldehyde. Aldehyde is activated by another coordinating chromium center. It will take this kind of orientation because of steric region, of course. So, R1 and X, they are in the anti. If you see here, if you give a rotation also, then you see R1 and X are anti in the zigzag, and ultimately after elimination you get this olefin where R and iodine are in the trans. So, E is the measure. Now, if you put another methyl group here, so it is 1,1-diiodoethane. With this you get a methyl group, and of course 8 equivalent is required, THF, DMF 25 degree centigrade 10 hours, you get this olefin, and here Ez is equal to 84:16. So, still E is the measure. Now, we will see Z selective Takai elimination. So, Z selective also possible because that intermediate if you make stable. So, we will see an example. So, when metahydroxybenzaldehyde is there, then the Takai elimination give this. So, E is still measured here, Ez is equal to 89:11, and when orthohydroxybenzaldehyde, that is a salicylaldehyde, then you get Z measured. So, we will see examples. So, this hydroxy group is important, and you can see this substitution you put like 2 substituted, that is the ortho here, and with fluorine, chlorine, bromine, iodine, all cases you get Z as the measure. Also, if it is 3 substituted, that is meta, or these same groups, also you see the Z is measured. Also, methoxy and CO2Me, if it is in the 3 substitute, only methoxy case you get little bit E measure, otherwise CO2Me case you get the Z measure. So, what is the region? What would be the selectivity factor here? So, Beilstein JOC 2017, this work was published. So, this could be the possible that for anti cases, this hydroxy is in the other side. If you see, this is anti and hydroxy, this one is on the other side. So, it cannot coordinate with chromium. So, this will be less stable, this one, and this will give this, of course, and this will give the anti. So, this will be trans product. Now, cis cases, this will be the intermediate, and this hydroxy is binding with chromium. So, this binding is very important. So, this is stable, and this of course will give this one syn, and this will give you cis product. So, that is the reason, because the hydroxy group is the ortho position, then it can coordinate with chromium, and that is why the Z intermediate is stable and you get the Z olefin. Now, we will discuss manganese based reagents in organic synthesis. So, manganese is a versatile stoichiometric reductant, chemoselective 1,2 addition also it can be used, conjugate addition to alpha beta unsaturated carbonyls. Manganese promoted cross coupling reactions and CH activation reactions, cyclization reactions, olefin functionalization reactions and epoxidation reactions. So, we will see now example, manganese is a versatile stoichiometric reductant. So, like Gigner reagent, the aryl or alkyl manganese also can be used for different reactions. So, we will see examples. So, unactivated commercial manganese powder is coated in a layer of oxide, so that is low reactivity. Examples of unactivated manganese 0 primarily in cross electrophile coupling exchange reaction, and organomanganese halides are highly chemoselective, various co-solvents can be used. So, they are not reactive like Gignard, they are much less reactive, so solvents like ethyl acetate can also be used, we will see examples. So, here an example of cross coupling reaction, cross coupling. So, here catalytic nickel is there and ligand N-octyl iodide. So, this is the N-octyl group will come and manganese 0 2 equivalent. So, in situ you generate the N-octyl magnesium and with DMPU solvent. So, this is DMPU. N-dimethyl propylene urea, and then 80 degree centigrade you get 82% yield for this product. So, this is very important. Additives such as TMS chloride, lead chloride, zinc chloride, iodine partially activate the manganese and expands its reactivity. So, here the zinc chloride is present, catalytic amount that enhances reactivity. Now, here this allyl bromide is present. So, allyl bromide will react with first manganese to generate the allyl manganese, and it will react with N-octanol with ethyl acetate solvent. So, this you see with ethyl acetate can be used as solvent, 60 degree centigrade, and here this one. So, this manganese is giving a reaction from the more substituted. So, more substituted carbon is adding to the aldehyde. So, you get a terminal olefin here. That means this more substituted carbon atom is reacting. So, methyl and this are the newly generated chiral center, and this was published in Tetrad Letters 1989. Also, a cyclic ketone can be used for the allylation. So, with allyl bromide, manganese 0, 4 equivalent, lead chloride and TMS chloride are added. Lead chloride only 1 mole % is enough, and TMS chloride 40 mole % THF 25 degree centigrade. You get this product in 99% yield. So, the allylation of the cyclic ketone, and this was also published in Tetrad Letter 1996. And we will see similar example to aldehyde addition, the aryl. So, this was allyl addition to aldehyde, and this is aryl. So, aryl iodide, that is the iodobenzene here with catalytic nickel, catalytic chromium, manganese 0, 1.7 equivalent, TMS chloride 2.4 equivalent, in DMF, DME 50 degree centigrade you get 67% yield. So, yield is little less for aromatic group, but still you get the product, and this was published in JACS 1996. Now, chemoselective 1,2 addition is also possible. So, the aldehyde can be reacted selectively in presence of ketones. Suppose here this dicarbonyl complex, this is aldehyde, this is ketone, and when you added this N-butyl manganese chloride in THF 20 degree centigrade, you get 89% yield for this product. So, selective addition to aldehyde over ketone. But ketone can also be reacted, that we will see later. So, this was published in Tetrahedron letter 1986. So, this is an example of ketone. So, ketone with this alkynyl manganese chloride in ether solvent room temperature 30 minutes, you get this alkyne group addition in 95% yield, and this was published or reviewed in Chemical Review 2009. Now, acyl chloride, earlier we have seen that copper can react with acyl chloride to generate ketone. Similarly, the manganese can also react. So, here this N-heptyl manganese chloride, when reacted with this acyl chloride in THF ether 66% you get this ketone. So, this is very important ketone, maybe this is low temperature. So, the ketone is further not reacting with this N-heptyl manganese chloride. So, you can isolate the ketone. This was published in Synthesis 1984. Now, conjugate addition, so far we have seen 1,2 addition. Now, conjugate addition also is possible to alpha beta unsaturated carbonyl. So, here you can see this is alpha beta unsaturated ester, 2 ester motifs are present, and this is manganese here. This is the vinyl manganese, and in THA minus 30 degree centigrade to room temperature you get the conjugate addition. So, this group is adding to this and you get this conjugated addition product, conjugate addition product. This was published in Tetrahedron letter 1989. Now, so far we have seen manganese as reagent. Now, manganese as catalyst also is possible. We have earlier told that like manganese can be also as catalyst. So, here you can see this reaction carbon derivative, and here with copper chloride 3 to 5 mole percent N-butyl manganese chloride THF 0 degree centigrade, this N-butyl addition is happening, conjugate addition. Without manganese chloride you get 51%. Now, if you put manganese chloride 30 mole percent, 95% yield you get. So, what is happening here? The manganese chloride is acting as a Lewis acid, and this was published in Organic Synthesis 1995. Now, we will see manganese in stoichiometric amount also and cross coupling reactions, alpha keto aryl chloride with Grignards. So, here it is interesting that you have a ketone group and aryl chloride. So, under this condition R2MnCl, the ketone group is not touched. So, ketone not touched, and selectively the aryl chloride is doing a coupling reaction and R2 is coming here. This was published in Organic Letters 2004, and you get high yield for this product, 70 to 90% yield. Now, manganese in catalytic amount also is possible, vinyl halides with Grignards. So, here this manganese chloride again is a catalyst here, and this is the Grignard R2MgCl, this is vinyl halide, and with manganese chloride 10 mole percent THF 0 to 60 degree centigrade, you get 50 to 90% yield for this olefin. And this is Ez ratio retained. So, if it is vinyl halide is E, then this geometry will be retained for most substrate. So, what happened? This magnesium of course is changing with manganese, and then it is adding, because simple magnesium, simple Grignard cannot add to the vinyl halide. So, only when it is activated with manganese, so this R2MnCl, this is forming, and this is adding to the vinyl halide. This was published in Organic Synthesis 2008. Also, radical dehalogenation cyclization reaction also is possible. Here N-butyl magnesium bromide and manganese chloride 10 mole percent, THF room temperature 80% yield of this cyclic compound you are getting. So, what could be the mechanism? So, most likely the metal halogen exchange will happen. So, here a metal, so suppose metal is here and O tert butyl. So, this will add here and this will, and the metal will come here. So, most likely manganese will be the metal there. So, what will happen? Put tertiary butyl, this. This will be manganese most likely, and this manganese can be removed then to get a terminal olefin. So, this olefin is generated here. So, this kind of mechanism is possible, that cyclization, and this was published in JOC 1997. Now, not only CC coupling, the CB bond formation is also possible. So, CB borylation. So, if you put B2 pin 2, so we know this is the structure. So, this is B2 pin 2, and with Cp star manganese tricarbonyl 10 mole % with carbon monoxide also you have to add additionally 2 atmosphere RH, that is aromatic or aliphatic. So, 76% yield for benzene, you get this bpene, and normal 1, 2, 3, 4, 5 pentane, you get this 35% yield. So, not only benzene, but the aliphatic also can be borylated. This was published in Angu on the Chemie 1999. Now, CS bond formation is also possible with manganese. Manganese chloride 20 mole %, phenanthrene you have to use 20 mole %, cesium carbonate 1.5 equivalent, and toluene solvent 135 degree centigrade. This thiol is adding to this aryl iodide, and you get this aryl thiol derivative, and different thiol can be used here, N-hexyl, here benzyl, here phenyl, and here also hexyl, and defined substituent on the aromatic ring is also possible, methoxy, hydroxymethyl, methyl, and you get moderate to high yield for this product. This was published in Chemistry Asian Journal 2013. Now, manganese catalyzed cross coupling. So far we have seen the CC, CB and CS. Now, we will see CN bond formation. So, amine also can take part in this cross coupling reaction with manganese fluoride 10 to 30 mole %, copper iodide 10 mole %, KOH2 equivalent, and this is cyclohexyl diamine, C-hex diamine 20 mole %, water 60 to 100 degree centigrade. This cross coupled product you can get. So, this is secondary amine is forming from primary amine, N arylation is happening, and this was defined amine can be used. So, here you can see this is the indole. So, indole was used here, this 2-iodopyridine, this is the N actually. So, this is the amine part, and here this is most likely the amine part. So, this is the amide. So, this is amide here. So, amide can also take part, and this product is forming 82% yield, this is 53, this is 94% yield. And this was published in European JOC 2013. Now, CH activation, we will see CH activation is also possible with manganese. First catalytic report using manganese. So, here this is the directing group, DG, directing group, and with manganese BrCO5 5 mole % with benzaldehyde, triethylsilane, toluene 115 degree centigrade, you get this kind of intermediate. So, this addition takes place to benzaldehyde from this ortho position, and this intermediate is formed where the manganese hydrogen is present, and with triethylsilane you get hydrogen elimination, and this OTS group coming here. So, this product is forming, so selectively ortho position, and this was published in Angu on the Chemie 2007. So, some more CH activation reactions we will see. Imine directed 4+2 benzynolation is possible. So, this is imine, this is alkyne with manganese BrCO5 10 mole %, dioxane 105 degree centigrade, 12 hours you get this product, bicyclic product. So, this is called benzynolation because this carbon is reacting to the triple bond and also the imine nitrogen. So, this could be the mechanism that first this kind of intermediate is forming, nitrogen and this CH is activated with manganese CO4. Now, triple bond will come with elimination of one CO. So, this coordination will happen. coordination. And now again another carbon monoxide may come, so you get the ring enlargement or ring expansion is happening here. So R1, R2, this is from the triple bond has become now double bond, and manganese is here, also will be coordinated with nitrogen. Then you get the product. So then you get the product here, so this will add. So this is like reductive elimination will happen. You get this, and this will react with starting material again to generate this, and after elimination of hydrogen, which can be detected also, you get this active intermediate. So this is very important, this triple bond activation by manganese, and then the ring expansion, and then the reductive elimination will give you the product. So this was published in Anglo and the Chemie 2014. Now we will see some manganese catalysis, carbon oxygen bond formation by CH activation. Like here, if you see this substrate, there is a benzylic group, this or this, these two are benzyl group. And when you treat with iodoxybenzene, pyridine, 10 equivalent base, and A, we will see the structure in H2O solvent, you get this hydroxylation. So this is hydroxylation, CH hydroxylation at the benzyl position, and you get 95% yield. So this is the structure of A, that is the manganese porphyrin, and R are beta cyclodextrin, and with this you get very high yield. So what could be the mechanism? The manganese 3 cell will be oxidized to manganese oxide here, amine double bond O, manganese will go to 5 now, because PHIO will oxidize, and now your alkane will come. So this most acidic hydrogen of course will coordinate with this oxygen, so that is the benzylic hydrogen, and after that R dot and OH will come here, and after that this, because this radical also stabilized by aromatic, that is the benzyl radical, and you get the ROH, and this you get back again. This was published in JOC 2002. Now we will discuss manganese halide catalyzed epoxidation reaction. This is also powerful reaction. The olefin, generally the cis olefin better for this epoxidation. You get this epoxide with 4 chiral ligand 4, you get 92%, chiral ligand 6, 86%. So these are the structure of chiral ligand. Mostly this is ortho para substituted, R2 mostly hydrogen or methyl, and you can see this Y can be PF6 or chlorine, and 4 is this one, R1 is tertiary butyl, so R1 R3 is tertiary butyl, R2 is H, and R4 is equal to CH2 whole 4. So this is cyclohexyl 1,2 diamine system. Of course trans one, so that the chiral will form, and this also you see tertiary butyl, R4 also this cyclohexyl. So what could be the, okay, there is another substrate, this one cyclic olefin, this is cyclic olefin, this is already cis configured, so here also you get very high E with 4, 86%, with 6 you get 91%. So today we have discussed first this chromium based reagents in organic synthesis. In chromium based reagents we have discussed nucleophilic substitution reactions of chromium arene complex, because this is electrophilic. When it is connected with chromium, that becomes the arene ring becomes electron deficient, so different nucleophilic substitution reaction can be carried out. Also you have seen ring lithiation. If you treat with butyl lithium, then different electrophile can be added. Chromium arene complex in asymmetric catalysis, we have seen different hydrogenation, Heck coupling, this chiral catalyst can be used. Also simple catalysis we have seen. Then chromium carbene complexes we have seen the cyclopropionation reaction. So there are ligand centered as well as metal centered reactions are possible. CC cross coupling reactions we have seen, and Takai olefination we have seen. In Takai olefination you get selectively E isomer, E vinyl iodide if you react with iodoform. Alternatively, salicylate derivative gives the Z olefin as the major product. Then we have discussed manganese based reagents in organic synthesis. So, manganese 0 a versatile stoichiometric reductant. So, manganese they are much more less reactive than the Gigner reagent. This can be used in solvent like ethyl acetate also, and different cross coupling reaction with aryl iodide can be added, and different coupling reaction, that is why CS bond formation, CB bond formation, CN bond formation can be carried out with manganese catalyst. Also chemoselective 1 to addition is possible. So, selectively addition to aldehyde motif in presence of keto group is possible. Also acid chloride addition will give ketone. That ketone, if you do a reaction at lower temperature, that ketone will not further react. Conjugate addition to alpha beta unsaturated carbonyls also we have seen that alpha beta unsaturated esters can be used as the Michael acceptor. Then CH activation we have seen the suitable directing group is there, then the CH activation is possible, like benzaldehyde addition is possible. Also triple bond the benzanylation we have seen. Olefin functionalization is also possible, that it can add this O lithium species or C lithium can add to the oxygen and you get the to the double bond, and you can get the terminal olefin and with a cyclic system. Also you have seen the epoxidation and hydroxylation. So, CH hydroxylation we have seen the manganese porphyrin and iodoxybenzene. If you treat with substrate having a benzylic CH hydrogen, that will be benzylic CH hydroxylation will happen. Also with manganese serine catalyst you can get the epoxidation, and particularly if it is cis olefin, then you can get high enantiomeric excess. Also cyclic olefins also you get high enantiomeric excess. Thank you.